the mass to charge ratio, mz, and I have my peaks on the spectrum. So as I said, the most stable fragment, sorry for the line, the most stable fragment, yeah, the most stable fragment will be the tallest line on the peak, the most stable fragment. And the molecular ion, so in when I go, let's go to the previous slide. So I told you that the molecular ion is basically the molecule with a +1 charge, because we have knocked one electron from the molecule. So in this case, the molecule was ethane. We knocked one electron from ethane, so we got an ethane plus ion, which is CH3 plus. So this is called a molecular ion because it is nothing but an ion of the molecule under consideration. So the molecular ion's peak will be the last peak on the spectrum. It will be the rightmost peak on the spectrum. You will not find a peak beyond it. You will find a peak beyond it, but we will consider when that happens. But for now, all you need to know that the rightmost peak on the spectrum is the molecular ion peak. So this is the molecular ion peak. It is represented as square bracket m square bracket closed. So you will also represent it like this in your papers. That's the technical way to do it. And I've written how we formed this molecular ion peak. I also explained it in the last slide. And you can just look at the mz value over here. And as I said, the mz will tell you the molecular mass of the fragment. In this case, the fragment is the molecule itself, the molecule under consideration. So whatever mz value you see here, it is the relative molecular mass of the molecule we are trying to analyze. So you will easily be able to identify the relative molecular mass of the molecule we are trying to identify. Let's move forward. So the m+1 peak. Now, as I said, the rightmost peak, I'll keep making, this time I will not waste time labeling the axes because you know what they are. I'll just write RA, which stands for relative abundance over here in percentage. RA in percentage and mz, mass to charge. So I said that the tallest peak would be the most stable fragment. The rightmost peak would be the molecular ion, which is the ion of the molecule itself, a +1 charge ion of the molecule itself. And then we have a very small peak, which is called the m+1 peak. So if you see a big peak on the right, it's not that big, but like relatively big, a relatively big peak on the right, towards the right of the spectrum, and a very small peak after that, and very small peak, just 1 unit right to this molecular ion peak, then it's called the m+1 peak. Now I'll tell you why this m+1 peak arises. So as we discussed when we were doing carbon-13 NMR, we discussed that the percentage abundance of the carbon-13 isotope is 1.1%. The percentage abundance of this isotope is 1.1%, which means that 1.1% of the carbon atoms in the molecule will have will be carbon-13 atoms. So we know that carbon-13 has one more neutron than carbon-12. So therefore it will have one atomic mass unit more than carbon-12 in its mass, because the number of protons will remain the same. It's the same element, carbon. The only thing that changes is the neutron number. The neutron number, we have 6 protons, 7 neutrons in this. We have 6 protons and 6 neutrons in this. So we have one more neutron in the carbon-13 isotope, and therefore we have therefore it is one atomic mass unit greater in mass than the carbon-12 isotope. So because it is only one atomic mass unit greater, we have a peak which is 1 unit to the right of the molecular ion peak, and that is called the m+1 peak. So whenever you see a very small peak over here, it will be the m+1 peak, and it indicates it's because of the carbon-13 atoms present in some of the molecules, in some of the sample, in a part of the sample. and therefore we have a peak over here because of it, because the mass is one atomic mass unit greater. So